This is a linear momentum example problem using a stationary deflector or blade. Uh, Looking at it from left to right, you have an inlet section here and an outlet section there. You have a liquid jet entering a control volume. Notice the location of the control volume includes not only the liquid but also the deflector or blade itself. Notice the x or y and x coordinates and the angle alpha that the liquid is turned. So now let's think through with numbers a practical problem. Here is the second drawing, and we're going to give you some givens. So, given what you're seeking to find. In this problem, we're given a mass flow rate that's equal to 32 kilograms per second. The entering nozzle has nozzle dimensions 2 millimeters by 40 centimeters. So this is a rather narrow that's not a very good drawing. Let's try that again. So this dimension would be 2 millimeters, and this dimension would be 40 centimeters. What we're looking to find are the reaction forces. So we're looking for Rx and Ry. The alpha, I should have said as well, is defined as 30 degrees. So how do we attack this problem? It's relatively straightforward, but we should be clear on the tools that are available to us. The first tool is conservation of mass or continuity. Those terms are synonymous. The other one is conservation of linear momentum. We might have Bernoulli at play. We certainly have energy in our toolbox as well. So how do we attack it? First, it's important to understand the velocities entering and exiting. As you saw up here, we assume that the velocity entering equals the velocity exiting. And that's because the pressures are not changing, the elevation is not changing. So from Bernoulli, we could say that the velocities don't change. Alternatively, we could say that the frictional effects along this surface are negligible. Either way, a key assumption in problems like this is that V1 does equal V2 in terms of its magnitude. Now let's approach the problem. V1, and I can say it this way, V1 equals mass flow rate divided by rho A1. So we should have been more clear too at the start that this is water. We know the density of water, and we also know the area of this nozzle. We're also given the mass flow rate. So therefore, we could write it out as 32 kilograms per second divided by 1,000 kilograms per meter cubed times an area of 0.002 meters by 0.4 meters. When you do that calculation, it ends up being 40 meters per second. So 40 meters per second, that's high speed flow ejecting from this nozzle. So to turn it, we'll take some force. Let's now figure out that. Well, what's the conservation of linear momentum from a Reynolds transport theorem perspective? It's a summation of forces acting on the control volume. Again, we should be clear that this control volume is identified at that location with this surface. So we're eager to look at velocities coming in, velocities going out, and asking ourselves, what forces would cause that velocity change? In this case, we won't be changing the magnitude or the distribution, but we will be changing the direction. So again, this is a Reynolds transport theorem idea, and it's partial with respect to t, rho, this is on the control volume. That would be the local change in momentum plus the integral over the control surface and in this case we will assume that it's steady state. So we'll make that explicit. Steady state, which therefore leads to an elimination of this term. We'll then focus here and decompose this. When we say decompose, we mean that this force vector and these vectors of velocity will impact the final result. So if we look at force in the x direction, again decomposed, is going to be equal to rho v1, and maybe I should make sure I stick with the positive convention first. So it would be rho v2 a times v2x minus rho v1 a v1x. F of y would be equal to rho v2a v2y minus 0, because as you can tell, there is no y direction of this velocity. Now to solve for f and x, fx and f sub y, which are our reaction forces, we can do the following. We can assume that in order to keep this blade or deflector stationary, we have to apply a force in the opposite direction that the fluid is flowing. We could also simplify these rho VA terms as the mass flow rate coming in. We could then write it the following way. And then this goes to 32 kilograms per second. V2x would be the same velocity coming in, as we said at the start, it doesn't change, times the cosine of alpha, which is in this case is 30 degrees, minus 40, direct substitutions. This value for Rx, taking into account we've assumed the direction, is 172 newtons. So that's pretty substantial for us to hold this blade or deflector stationary as you're hitting it with 32 kilograms per second of water at 40 meters per second. To finish off the problem, to push something up into the y direction, we certainly have to apply a force in that direction. So we'll have this final equation, m dot v2y minus v1y, which again we said was 0. Putting in the numbers, you have 32 times 40 sine 30, which equals 640 newtons. So these are the two final answers for this problem. And in review, let's go back up. We were given a mass flow rate, an alpha, a nozzle diameter, and, although I didn't mention at the start, that this is water. We were then asked to calculate the reaction forces, and we thought to ourselves, what tools do we have? We went through conservation of mass, conservation of linear momentum. We also thought, why don't we throw in Bernoullian energy just in case if we get stuck? We solved for the velocity coming in since we knew the mass flow rates, the density, and the area. We applied the Reynolds transport theorem for linear momentum, recognizing that it was steady state. We decomposed the problem into an x direction and y direction force. We finished up by calculating those forces, Rx and Ry. I hope this has been useful.